I got excited. All right. I introduce to you FrODO. Perfect time for pictures. Fractional order, distributed optimization. By me, AndreiLix, Marcel van Heerve, present here in the live stream. Happy birthday, Marcel. Sergio Pequito from University of Lisbon. All right. Why is my project important? So, we have a bunch of hospitals, all right, holding a bunch of medical data. We want to do deep learning on that data, make some lung cancer classifier to ease the radiologist work burden. Now, the problem is that this data, patient data, healthcare data, is highly sensitive because of obvious privacy concerns, such that we cannot aggregate it to a huge server somewhere on some machine learners, on some machine learning engineers' basement, and just train the model there. So if we cannot get the data to the model because of privacy issues, then we can get the model to the data. And with distributed optimization algorithms, we can achieve precisely this by sharing copies of the same neural network across hospitals. And using distributed optimization algorithms, we can train those networks in parallel by them communicating non-sensitive information and eventually achieving the same performance as if we would aggregate the whole data on the same server. All right. Now, still open problems in this field. Ill-defined Hessians. Performance. These algorithms are sensitive to ill-defined Hessians. I'll explain you guys what that means later. And also non-convex optimization when your optimization function is non-convex. I'll also show you guys how that looks. Okay, so this all started from control theory, from the fact that there is a huge field for control theory that tries to solve a super similar problem to what machine learning optimization tries to solve. And here we see the similarities between the control model and gradient descent. So we have a parameter, and it gets updated based on the previous error, weighted by a certain weight. Same as in gradient descent, we have this agent, and we update it based on the previous error on your objective function, parameterized by the step size. Now we found a control model that incorporates some fractional derivatives, to which we'll get later, that has super good performance compared to the previous state of the art. And we tried to do that, take this control model and put it in machine learning, adapt it, tailor it for our distributed purposes. Fractional derivatives, what does this mystical thing mean? So we know what the first order derivative is. Let's say for position, we have velocity. That's the first order derivative of position. And then we also have a second order derivative, which is acceleration. Now, what lies between a first and a second order derivative? What is the mathematical transformation that, say, if you apply it twice, you get the equivalent of a derivative? Can you have such a thing as a 1/2 order derivative? The answer is yes. And this type of derivative has interesting properties because it functions both as a usual derivative, giving you local information about the slope at a particular point, but also non-local information about the slope of your function in the vicinity of your local point. All right. This is an illustration of how this memory is weighted based on how far your neighboring points are from your current point. You assign less and less weight to them based on the fractional order. All right. Okay, so we incorporate this in a memory term, which keeps tracks in the optimization process of previous gradients we encounter. All right. This is the implementation of our algorithm. We start with an initial agent alignment because we have our network, let's say our hospitals starting up with their freshly initialized neural networks. We want to make sure that the neural networks start with the same parameters to ease the stability of the optimization process. Then we come to the descent terms, the gradient, much like in gradient descent, and then the memory feedback with the fractional shenanigans. And then we update the agent states. All agents, all hospitals optimize their local functions. And finally, we align them right back such that we have one singular model. Now, this is the ill-defined Hessian setting in which, and why is this a problem in machine learning? Well, because if we start on here, on this point, this orange point in the left, then we only need, let's say, 5 steps to get at the optimum. But if we start here at the orange point up top, then we will need 1,000 steps because the optimization space is way flatter. And here it's way steeper. So given a fixed step size, you need to take more steps to arrive at the optimum. All right. Here we show that our fractional long-term memory, helps with the stability of the optimization process under this ill-defined Hessian condition. So with blue, I have my algorithm staying super stable across different initial conditions. And here I have with orange short-term memory like in heavy ball and no memory like in gradient descent. These prove to be super unstable, which hurts the optimization process. All right. All right. The non-convex setting, here we use the Rosenberg function. So this is not a nicely defined function in which you just go down the steepest gradient. This is a funky looking optimization space, non-convex, the technical term. All right. And again, the performance. My fractional method proves to be in edge cases to have 3 orders of magnitude fewer iterations needed to converge than the short and the no memory cases, which was pretty cool. All right. And now, what we're all here for, neural networks. We tested this in an actual use case similar to the hospitals in which we send actual neural networks and we want to optimize them, not the toy settings in which we only have 2 parameters. We have 2 ANNs functioning as 2 hospitals. Their private data sets, let's say the lung scans private to each hospitals, 1 million parameters each, standard scene and setup. Now, Adam still kicks our ass, but here with green, but we achieve better convergence than Adam and all the other memory-based baselines we tested, which is pretty cool, if you ask me. That we achieve better convergence, albeit slower than Adam. All right, this was it. I have some appendix with the actual convergence proofs. Important to mention, convergence, yes, it doesn't only work in practice, but also in theory. I have the math, prove that. Very important. Okay, this was it. I like also to take the occasion to thank the Alice Radboud community for facilitating FrODO, the birth of FrODO, my supervisors, Marcel Fanjeva and Sergio Pequito, and my Alice colleagues, without which I probably would have taken a one-way ticket to Romania and never looked back on the AA journey. Nice. All right, thank you. So the equivalent. Okay, so back to the circle. So we have 4 agents, each with its own private objective function. So the agent 1 has this as its private objective, agent 2 has this, and their sum, the global optimum, is what we actually try to achieve, the red dot. Okay, so this is the different objectives, indeed, different loss functions. Now, in the ANN setting, the different objectives correspond to different data sets, because that's where you get your learning signal. And in the hospital real world case, the hospitals have different data sets which correspond to which, let's say, correspond to different objectives. All right. Okay. Go ahead, mate.
You mentioned that so the idea of this is to train a neural network across multiple hospitals, right?
Yeah.
And so when you use it later on the slides, do you do that?
Okay. So this, of course, from the comfort of the uni GPU cluster and my laptop. There is no hospitals involved here yet. But the computational graph is equivalent to as if it was made by different hospitals. So computationally speaking, if I had all the same data sets on my computer or two different hospitals on two different computers, the algorithm would make sure that the exact same thing happens.
But if you say you use it across different hospitals, do you think latency?
Definitely.
No.
But that's, yeah, so again, to my colleague's point about standardization, this, again, a big area, as far as I found, that needs some commonly agreed upon benchmarks and standards of practice, because even to figure out the computational graph people use to make their algorithm work would need hands-on experimentation, just to figure out the order in which they did to make the algorithm work. Because this stuff with all the latency and the order in which you can do the alignment or you can do the descent, this all needs to be in synergy with your optimization method. Yes. Advice? Oh, go ahead.
You're modifying the loss function to take in these different agents that are there, let's say they're chunks of the data, and you're aligning the.
Exactly. Yes. Because the agents communicate their parameters to each other. Not their data, super important. The data stays private, safe kept by the hospitals, but they communicate their parameters between them. And based on the weight they give to each neighbor, which also includes many subtleties about which neighbor to weigh most based on their effect on your objective, then they optimize, then they align.
Like if you
Yes. So the fractional order solves this problem of the ill-defined Hessian, because this is super prevalent in neural networks. When you look at your optimization space, it looks kind of like this. It's not a well-defined, perfectly convex optimization space. It's a squished and distorted space in which this proved to be super stable given the long-term memory. Now, let's see if we get a bit more technical. This is called chatter in control theory. When your algorithm overshoots the minimum and then oscillates until it gets the minimum, this is called chatter. And this is partly what makes the algorithm more stable. Because of the long-term memory, you don't do perfect optimization. You do the chatter, you oscillate a bit, and that's why it takes longer when the starting point is steeper, because it overshoots, but then it catches up in flatter initial conditions with this long-term memory. All right, good question. So this is one iteration of the optimization process. So just like gradient descent, you start off with your initialization, you have your learning rate. Based on that learning rate, you take a step, and then you continue. Here we do the same thing, but so first we make sure the agents are aligned. We start off with agents at the same point. Then we compute each agent's descent point, private descent. Then we update the agents. So once we're computed, the agents spread out, and then we align them back again. So this is one iteration. And we do this multiple times, and eventually we have the global minimum.